viewers, welcome to CEC lectures. Myself Dr. Preeti Tagwani from Department of Computer Science, Aryabhatta College, University of Delhi. So presently we are going through the topic of scheduling algorithms, and we have already seen within this series of operating system concepts that in order to schedule the CPU for various jobs or for various processes, we have many strategies, various algorithms are available, and each and every algorithm is having different properties, and choice of a particular algorithm is going to favor one class of processes over the another. So basically what I'm trying to say is we have kind of criterias, those have been suggested for comparing some CPU scheduling algorithms. What are these criteria? Let us kind of begin with this quick recap, and then we'll proceed with the today's agenda. So in order to kind of opt for any of the CPU scheduling algorithm, we want to maximize the CPU utilization and the throughput, and these are the terms which we have already kind of seen in detail in our previous lectures. Also along with this, we want a fair allocation of CPU to be kind of to happen among various processes. Also we want to minimize turnaround time, waiting time and minimum response time. And with all these set parameters, we have also seen some of the scheduling algorithms like first come first serve, shortest job first and priority scheduling that we have already seen. So in this lecture today we are going to see more of the we can say scheduling algorithms, and the first one of them is longest job first, that is the LJF. So longest job first is opposite of the shortest job first thing, and as the name suggests, the process with the largest burst time is going to be processed first. That means the longest job will be given the CPU or allocated the CPU first, and it is basically non-preemptive in nature. So what are we going to do in this longest job first policy? That among all the processes waiting in a waiting queue or waiting in a, we can say, ready queue, CPU is always assigned to the process which is having largest burst time. In shortest job first, we were looking for the shortest burst time, but here opposite of SJF, we are looking for the largest burst time. And if there is going to be any tie, that means two processes, let's say PI and PJ, are having a similar burst time, then this tie is broken using FCFS, which is first come first serve. That is, the process which is arrived first is processed first, or is kind of first allocated the CPU. Now LJF you can implement, although basically it is kind of non-preemptive in nature, but you can also have the preemptive version of this LJF CPU scheduling. So that means we can say the LJF is going to have both versions of it type, like preemptive and non-preemptive type. Now by this time you must have guessed that what are going to be the disadvantages of this LJF policy. So first thing, it may lead to a very high average waiting time, because average waiting time is what is the sum of waiting times divided by number of processes, and this we have already seen earlier. And in shortest job first, this is kind of very small as compared to other policies, because the first one is the we are taking the processes according to their shortest burst time first. So the other processes are waiting little less, but here in LJF, if we are going to take the largest job first, then the processes which are behind in the queue will need to wait more. So this is going to give us a high average waiting time, and also the average turnaround time for a given set of processes is also very high. And because of kind of this policy, some jobs may lead to starvation, and this starvation is also known as the another term for this starvation is the convoy effect. So this largest job first policy we can say is a kind of a little less preferred, but yes, there could be some scenarios where you need this. Now coming to the next policy, which is round robin policy. Round robin policy is, we can say it is the most widely used. Your Windows is also using this round robin policy. So in this round robin policy, this or we can say this policy basically focuses on the technique of time sharing. Now, how the time of CPU is going to be shared between the processes. Let's say we have P1, P2 and P3, three processes with their burst time, and we have decided one particular time quantum. One time quantum has been decided, and that time CPU will be allocated to each and every job for that particular time quantum. Let's say 3 seconds, for example, 3 milliseconds. So P1 will be taking it for 3 milliseconds, and then it will come out of the CPU execution thing. And if P1 needs this thing more, CPU is kind of more required here. So this is going to join a queue again, and this is a kind of, you can say, a circular queue. So if you can look closely to this round robin policy, we can say it is a preemptive version of FCFS, which is first come first serve. And what are the other characteristics? So before going into other characteristics, let us try to understand how this is going to happen. So if you can see on the screen, we have three processes, P1, P2 and P3, and on the right hand side there are given the burst time. Let's say these burst times are in milliseconds. So P1 is looking for 24 milliseconds, P2 is looking for 3 milliseconds, and P3 is also looking for CPU only for 3 milliseconds. So now what your operating system needs to do. Your operating system first needs to decide on a particular amount of time quantum. So let's say the time quantum here is going to be 3 milliseconds. So what will happen? Each and every process is going to take the control of CPU for 3 milliseconds till it is going to be kind of terminated after completion of its execution. So for example, if you can see the giant chart which is given on the or we can say the schedule chart which is given on the screen. So we have P1, P2. So from kind of 0 to 3 seconds. So first 3 seconds of CPU are allotted to the process P1. Then even after getting the CPU for 3 seconds, your P1 is still left with the burst time of 21 seconds. So that means P1 still needs more CPU. So then in that situation, what will happen? In that situation, P1 is going to join the ready queue again. Now P2 is taken from the ready queue and given the control of CPU for 3 seconds. Now after this 3 seconds, here P2 basically is done with its own burst time, and now P2 is not looking for CPU anymore. That means this P2 is not going to join the ready queue. It will be kind of out of this ready queue, and it will start with other processing of itself, and then so on and so forth. After P2, there comes P3. The P3 is also looking for the CPU for its burst time, which is equals to 3 milliseconds. So P3 is now given CPU for, let's say, 3 milliseconds. Now after this, P3 is also not requiring CPU anymore. Now it is only P1 in the queue which is looking for CPU. So starting from 10th second to the beginning of 14th second, then from 14th to the beginning of 18th second, and then so on and so forth. Every time it's P1 who is kind of getting into the queue again and again, and getting the CPU for its allocated time. So basically what is happening here, kind of we can say a circular queue is maintained of the jobs or of the processes which are looking for CPU for some time, and each and every process is given the CPU or given the control of CPU for some particular amount of time, which is more commonly known as time quantum. Now this time quantum is actually decided by your operating system. So time quantums should be such that neither it should be kind of we can say very large, nor it should be very small. So if there is going to be a large time quantum, then the processes which are behind in the queue may lead to starvation, and if the kind of your time quantum is very less, then there will be a lot of fluctuation, we can say. And what fluctuation I am talking about here is the context switch. So CPU, a process is taken from the ready queue given to the CPU. CPU which was already working on some other process is going to release that particular process, and that process will again join in the that circular queue. So in this way, if we are going to kind of have a very less amount of time as its time quantum, this context switch will be kind of very we can say occur very frequently, which is not this is going to we can say reduce the throughput, and the total response time will be obviously we can say increased. So we have to be, or the operating system will need to decide, or this is a we can say it's a research decision or it's a policy thing, that how much time one should have in as its time quantum. Now after understanding this policy, if we talk about the characteristics of this round robin policy, we know that if we talk about average waiting time, it is often long if compared to shortest job first. So with this example which we have just seen with three processes which are P1, P2 and P3, let's try to calculate the amount of waiting time the processes are waiting, or let's see how much average waiting time is going to be here. So P1 is going to wait for let's say some 6 milliseconds, which is 10 minus 4, and then it is continuously P1 which was executing. Then P2 is going to wait for let's say 4 milliseconds before P1 has got its first time quantum, and P3 has kind of waited for 7 milliseconds because till 7 milliseconds it was the time quantum which was given to P1 and P2. So if we are going to kind of sum up this 4, 7 and 6, so 6 milliseconds for P1, P2 4 milliseconds and P3 for 7 milliseconds, and we are going to divide it by 3, the average waiting times comes up at 5.66 millisecond, which is, yes, I can say a little higher. But on the very other hand, we can say it's a very kind of what we can say about this, the characteristics of this particular policy is this is kind of a policy which focuses on the fair allocation of CPU, and fair allocation of CPU was also one of the characteristics or one of the parameters of looking for the CPU scheduling algorithms. So whatever algorithm we are looking for, or whatever algorithm we are opting for for the scheduling of CPU, that needs maximizing some parameters, that needs minimizing some parameters, but apart from this maximization and minimization, that also needs the fair allocation of CPU. And yes, we can say that this policy, which is round robin policy, is going to give a fair allocation, or is this going to kind of raise, or this is going to focus a fair allocation of CPU. Also, it is considered as primitive as the processes are given to the CPU for a very we can say limited time, and then they relinquishes the control. But it is one of the most widely used methods of CPU scheduling as a core, and as I have told you, various versions of Windows also uses this CPU scheduling policy of round robin thing. Also, if you can see, it is very simple and easy to use and easy to implement, because the jobs are kind of, we can say, are getting moved inside a particular circular queue. Though that circular queue as a data structure of process control blocks has to be maintained. Also, one more important characteristics of this policy is this is a starvation free policy, because all the processes are getting some balanced CPU allocation. So this is a very important characteristics if we talk about the round robin policy, that it is a starvation free policy. It seems to be fair as every process is getting an equal share of CPU. Also, if there is a process which is kind of newly created, then what will happen to that process? If we think about it, then that newly created process is added to the end of the ready queue, and sooner or later it is going to have its own time quantum, or it is going to have its own particular time slice for which the CPU is allocated to that particular job, if we can see. So with this, let me recap what we have taken in this lecture till this point. So we have started with a quick recap of why the CPU scheduling algorithms are required. So in order to maximize some parameters, in order to minimize the response time and waiting time and so on and so forth. And then we have seen, today we have seen one round robin policy, and another one was the largest job first, which was LJF. Now with this, and we have also seen the characteristics, pros and cons of both the scheduling algorithm. Now with this, let us explore one more CPU scheduling algorithm, which is multiple queue scheduling. So multiple queue scheduling says that there are many processes in the ready queue, and these processes can be divided into different classes, or we can say different queues, where each class has its own scheduling needs. So for example, if you can see on the screen, we have three class of processes. One class is the system process, another class is the interactive process, and the third class is the batch process. And what we have done with these classes, that each and every class of processes is given or is assigned a separate queue. So if you can see, the system processes is assigned let's say Q1, then all the interactive processes are lined up in Q2, and all the batch processes are lined up in Q3. And how we have we can say arrange these processes is from their high priority to low priority. So here in this figure, we have system processes which are arranged in Q1 are having the highest priority. Then Q2, which comprises of all the interactive processes, is having lower priority as compared to the system processes, while the last one, which is available in Q3, all the batch processes are having very little, or the least priority, we can say. So all these queues of different processes are arranged according to their priority. Now these are, we can say, multiple queues or multi-level queues. Now what are we going to do with these queues is, we are going to schedule processes contained in these queues differently. So for example, an interactive process here could be a foreground process, and a batch process here could be a background process. And now let us try to understand that these two classes are having very different kind of scheduling needs, and for these type of scenarios where the processes which are available in ready queue belongs to kind of different classes, and these different classes are having different scheduling needs. In these type of scenarios, we are going to use multi-level queue scheduling. So what are we going to do in this? These processes are permanently assigned to one queue. Now why I am insisting on the word permanently? Because that is going to give us that this is going to open the gate for the next scheduling algorithm. So processes are permanently assigned to one queue, and which queue these processes will be assigned, this decision will be based on some property of the process. Now which property of the process I am talking about here? It could be memory size, it could be process type, or it could be process priority, or it could be kind of level of interactivity. So the background processes needs no interactivity, while the foreground processes needs interactivity, and then so on and so forth. Now after having or after arranging these different classes of processes into different queues, we are going to have different scheduling algorithm for each and every queue. So as we have seen in the figure, that system processes within the queue 1 are having kind of we are assuming here, or this is the criteria under which these processes are separated. So system processes are having their different scheduling needs from interactive processes, while interactive processes are having their different scheduling needs from which are different from batch processes. So in this situation, we have that each queue is having its own scheduling algorithm. For example, we can say that the foreground queue may be scheduled using a round robin policy algorithm, while the background queue is scheduled by a first come first serve algorithm. And also when we talk about the priorities here, so we have these queues starting from high priority to low priority. So what is the kind of significance of this priority is the queues with higher priority will be kind of, we can say, executed first, and when there is no process in the queue of higher priority, then only there will be a turn of the processes which are arranged in the low priority queue. So basically with this example, I can I can elaborate it here as no process in the batch queue could run unless the queues for system process and interactive process were all empty, because the system process and interactive process queues are having high priority. So even if an interactive process entered the ready queue while a batch process is already running, the batch process would be preempted. So that means this policy is completely based on the preemption, we can say. Another possibility or another idea could be is to assign some time slices for the queues. So if you can see on the screen, we have three queues here: system, interactive and batch queues. So can we do something of that sort, that 30% of the time the CPU is given to system processes, then for maybe some again for 40% it is given to interactive processes, and whatever is left, let's say 30% time, it is given to the batch processes. So that could be another idea, or one idea could be let's finish with all the processes in the Q1 first, then all the processes in the Q2, and then there will be the turn of all the processes in the Q3. So another possibility is to time slice among the queues, where each queue is going to get a certain portion of the CPU time, and that CPU time, that particular queue is going to schedule among its various processes. So with kind of this platform, we can say there could be advantages of this multi-level queue scheduling and also the disadvantages. Let us see what are they. So the main merit of multi-level queue is that it has a low scheduling overhead because of the separation of the classes of jobs, while disadvantages if we talking about is starvation problem could be there for low priority queues, and also it is inflexible in nature, as in one process which is going to enter in Q1 or one process which is going to enter in Q3 will not allow to get an upgrade to Q2 or to a higher priority queue. So with this we have understood this multi-level queue scheduling, and in this lecture we have seen 3 CPU scheduling algorithms which are longest job first, then round robin policy and multi-level queue scheduling. So here is a list of references which is being used for the preparation of lecture. Thank you for a patient hearing. See you in the next lecture. Till then, take care. Goodbye.